Good morning, everybody, or afternoon, as it were. Every so often in the semester, I like to try something a little different, and what I thought I would do for our Tuesday class is to hold class online. What that means is that I'm going to be narrating this lecture that I would have given in class, and you can watch it anytime that you want to. And if you have questions about it, then you can ask me about that either on Canvas, through email, or in person. One of the things that I really like about doing online lecture class sorts of things is that you can watch it as many times as you want to. So if you're going through and trying to study the material, you have a set of information to work with. Obviously, it makes it harder to ask questions in the moment. So if you have questions while you're watching, write them down, and I'll answer them however you decide to approach me later. But what we're going to be talking about actually is hypothesis testing, and we're going to be talking about some of the logic that underlies hypothesis testing. Before I get into that, though, I want to briefly recap kind of the main idea from last class, and I'm not saying that this is all you need to know about last class. I'm saying that this is what you need to know going into this idea of hypothesis testing. So let's see if we can get this to work here. Alright, I paused briefly to make sure it was working. It seems to be, so let's continue. To recap from last class, what we do typically when we're doing statistics and hypothesis testing in general is we make an assumption that most variables in the population are normally distributed. Up until last class, we were talking about raw score distributions. So let's say that we asked a bunch of people living in Allentown how frustrated they are with driving in Allentown. We could come up with some, on a 1 to 9 scale, with 9 being the highest, 1 being the lowest. We can come up with some mean for that estimate, and it would likely be normally distributed. If it's not, that's okay, because as we talked about last time, as long as we're using a sampling distribution of means, then we can start with a population that's not normally distributed. But when we're dealing with a raw score distribution, we define it by mean and standard deviation. So as an example, like it says here, this is frustration with driving in Allentown. And now when we're doing statistics, we're moving into instead of a raw score distribution, what we call a sampling distribution. And instead of this being a distribution of the actual ratings of people's frustration with driving in Allentown, what it is it's a distribution of means when we take a sample of 10 at a time. So we ask 10 people, how frustrated are you with driving in Allentown? We get a mean score for that. We ask 10 more people, we get another mean score for that. And you'll notice that this distribution tends to be narrower because when we're dealing with means, we tend to have a more precise estimate of what it is that we're talking about in terms of means for something. When we're trying to estimate something, it's better to get a distribution of means than using all the raw scores because the raw scores contain extreme values. And so what we're doing here is we're defining the distribution by the mean of means, which turns out to just be the mean of the population, just like the raw score distribution. But now we're talking about variability in terms of standard error instead. So standard error is actually the variability within that distribution. Standard error tends to be smaller by definition than standard deviation, and this will always be the case as long as you have a sample that's greater than 1. So that might be one of those random test questions that I ask you, like which is bigger, standard deviation or standard error? And the answer to that is as long as you have a sample size that's bigger than 1, standard error is always going to be smaller. So when we're thinking about a distribution, we can think about standard deviation as how wrong or uncertain we are. So for trying to figure out, okay, so how frustrated are people with driving in Allentown? Like, what is the population average? Is there something we should do about this because people are frustrated with driving in Allentown? When we're trying to make that decision, we can use a standard deviation as an estimate of how inaccurate we might be. So here the average might be 7.5 with a standard deviation of 0.5, And if we're trying to assess the 95% likelihood, and again, we haven't talked about this in terms of confidence intervals, but that's what a confidence interval is what is the 95% likelihood of the mean for this particular situation? And here it looks like the 95% likelihood would be somewhere between maybe 6.75 and 8.25, 8.35, something like that. So what this tells you is the middle, and it tells you, I think my mean is 7.5, but I acknowledge that there's some variability here, and maybe my sample wasn't really accurate 100%. But when dealing with raw scores, if you measure one person, then this is the distribution you'd be working with. When we sample a distribution of means instead, the variability shrinks because we're dealing with standard errors now, and the more people that we sample because of the central limit theorem, or because of just the fact that the more people we sample, the more accurate we tend to be and the more confident we tend to be, there's less likelihood of error. So when we're asking, for instance, how frustrated are people with driving in Allentown? If we take a sample of 25 people, we're going to be more confident than if we took just a sample with one person. And we'll be more confident still if we sampled 100 people. So, in short, there's a benefit to sampling more than one person. And that benefit is when we're trying to estimate what the mean actually is, we tend to be more accurate about it. It turns out there's also additional benefits to this that we're going to talk about later when we talk about power and p-values and all that stuff. And this brings us into our discussion of hypothesis testing. So this is week 8's content, if you will, or chapter 8's content. So what is a hypothesis? What is a hypothesis test? How does that logic work? And I found in the past that students tend to struggle a little bit with the logic behind hypothesis testing, and the reason for that is because it's backwards, quite frankly. When we're doing a hypothesis test, we're testing the null hypothesis, essentially, and trying to make some conclusion about a research hypothesis. And we're not actually showing support in favor of a research hypothesis, we're showing support against a null hypothesis, which sounds very backwards, granted, but let me get into some nuts and bolts of this, and then I'll explain what I mean. So a hypothesis is a tentative statement about the relationship between two or more variables, and we can state a hypothesis abstractly. So for instance, we could say regular exercise will increase health, and the reason I call this an abstract hypothesis here is because we're not really stating specifically what we expect to happen in terms of a relationship between two variables, for instance. And we're not saying, for instance, how much regular exercise is, or how are we measuring health. Down here, the concrete definition, which tends to be more precise and preferable, particularly in this class, is when you're stating specifically how you're operationalizing each of your variables and how they're going to be related with each other in your hypothesis. So here the concrete one might be jogging for 60 minutes a week versus not jogging at all will reduce systolic blood pressure. So we can do a study where we have people jog for 60 minutes a week, and then we observe people who don't jog at all and look at their systolic blood pressure. And we would expect that the systolic blood pressure would be lower for people who jog 60 minutes a week compared to who don't jog at all. And of course, there's other issues like, well, what about other kinds of exercise they're doing, or what about people who have bad knees or something like that? And obviously, it's not a perfect hypothesis, but it's something that's concrete that we could, do some sort of a test on. So concrete hypotheses, they're stated in terms of operational definitions between two variables. In words, it says jogging for 60 minutes a week versus not jogging will reduce the systolic blood pressure. Importantly, we can also state the concrete hypothesis mathematically, because what we're really saying here is that we're going to look at a group of people, and we're going to look at their average of their systolic blood pressure for those who jog, and we're expecting that it's going to be lower. In other words, they're going to be healthier than the average of the systolic blood pressure for people who don't jog. And notice that I'm using parameters here because your hypothesis is making a statement about the population. It's saying, what do I think is true in the real world? And I'm saying, I think that if you jog, you're going to have lower systolic blood pressure than if you don't jog. And we're going to use a sample to test that. And this goes back to the idea in Chapter 1 of descriptive versus inferential statistics. Because oftentimes when we're doing statistics, we're trying to collect information from a sample to make a conclusion about the population. So that's why the hypothesis makes a prediction about what's true in the population, and then we use what we have in the sample to try and see if it's true. Or likely, rather. Psychologists predominantly use null hypothesis significance testing, or NHST. What is this? There's actually quite a bit of controversy about null hypothesis significance testing, and I'm going to talk about that as we get a little bit further. Basically, what null hypothesis significance testing is we test, we assume a null hypothesis, and then we record a sample and get some observation. And if that observation, given the null hypothesis, is really unlikely to happen, then we reject the null hypothesis and we say it's probably not true and that there's probably something else going on. So let's break that down a little bit. Component 1, the null hypothesis. For any research hypothesis, there's a null hypothesis, which states what the research hypothesis is not. So here in words, the research hypothesis is jogging for 60 minutes a week versus not jogging reduces systolic blood pressure. The null hypothesis is jogging for 60 minutes a week versus not jogging does not reduce systolic blood pressure. And you don't typically include it in all caps here, but I have that for emphasis just to show that all you're doing is taking your research hypothesis and saying does not. Notice that you're not saying, for instance, jogging for 60 minutes a week versus not jogging increases systolic blood pressure. You're not saying that because that would be a different research hypothesis. The null hypothesis is simply whatever it is that you're hypothesizing, it's the no, that won't happen version of it. In math, we can say this as, so here's the research hypothesis from earlier. The mean for joggers will be less than the mean for those who don't jog, the not jogging condition. The null hypothesis, mathematically, is everything else that the research hypothesis isn't. So in this case, because we're predicting that jogging will reduce systolic blood pressure, the null hypothesis equates basically to jogging either won't change or it will increase the systolic blood pressure. So it's the null hypothesis in that whatever we observe will be evidence for one versus the other. So moving right along, here's some significance testing fun here. Here's a nice picture of the standard normal probability density function, and for those of you who have taken calculus, maybe you've seen this function before. It's just a normal distribution, and you can see that on the bottom, on the x-axis, are z-scores. Essentially, this is the distribution of if the null hypothesis is true. If the null hypothesis is true, it's very likely that we're going to observe something that's consistent. We're going to observe that people who jog have a very similar systolic blood pressure than people who don't jog, and that's why at z equals 0 is the most common observation. If the null hypothesis is not true, then we would expect to see something out in the tail ends of the distribution, which are actually very unlikely. So if we, for example, observe that joggers have 3 standard deviations or standard errors higher of systolic blood pressure, we would say, well, this doesn't seem true then. It doesn't seem true that jogging has no effect on systolic blood pressure. Same with if we observe something that's 3 standard errors below, we would say it's very unlikely that jogging has no effect on systolic blood pressure, and therefore we would conclude it seems that it does. So the guidelines for statistical significance, it's very unlikely to happen in this distribution where the null hypothesis is true, but it happens, we say that it's statistically significant. So you've probably heard the term statistically significant before in psych papers. What they're basically saying is that we observed something that was very unlikely to happen if our hypothesis is wrong. How unlikely should is very unlikely. I don't know why it says that. How unlikely should be very unlikely. So we want something that's very unlikely, but we have to, going back to this distribution I just showed you, how far away does it have to be in order to be very unlikely? And I asked you guys the other day about the coin flips. So how many heads in a row would I have to flip in order for you guys to be suspicious that there's a trick coin being used here? And each of you had differing answers, and oftentimes psychologists have different answers to that question. But generally speaking, we say if it's less than 5% likely to happen, so a 1 in 20 chance, then we say that it's statistically significant. The probability that we use as a threshold in this case is indicated by alpha. So the probability of something that we need in order to reject the null hypothesis and say something's going on here is indicated by alpha, and typically alpha is set at 0.05, but it can be anything. It could be 50%, for instance. I don't know why you would want 50%, but it could be. So let's go through an example to make this a little bit more concrete. Hopefully this will help clarify a few things, because up until now I've been talking about this in a very abstract sort of way. A researcher believes that his new multivitamin will cause people to be smarter. He knows that IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. He pulls a random sample of 25 college students from Muhlenberg and gives them the multivitamin, then measures their IQ scores, which turns out to be 114. Is the researcher's hypothesis supported? Test with a 5% significance level. So alpha equals 0.05. When you're reading this, you start doing practice problems that are associated with this. You're going to see some numbers, and you're going to have to learn what to do with those numbers. And hopefully some of you are already kind of thinking ahead, like, okay, he said there's a mean of 100 here. What is that? And there's a standard deviation of 15. What's that? What do I do with that? And there's a sample of 25. I have to do something with that number. And all these numbers are going to be relevant. Let's work through this one as an example so that we can see. The first thing we need to do is state what our hypothesis is. So the research hypothesis is students who take the multivitamin will have higher mean IQ scores than the typical mean IQ score. The null hypothesis, remember, is the not version of that. So I've taken the research hypothesis and I literally copied and pasted it, and then instead where it says will have higher mean IQ scores, it says will not have higher mean IQ scores. Pause this for a second and try to write out the research and null hypotheses in math terms. So hopefully this is what you've come up with for the research and null hypotheses. The research hypothesis states that the multivitamin's going to increase IQ scores, essentially. The mean IQ scores will be higher for students who take the multivitamin, so we have a mean here, and I have multivitamin in subscript, because that's who we're talking about. It's going to be higher than the control condition, or those who don't take the multivitamin, or in this case, the average IQ scores. The null hypothesis is everything the research hypothesis isn't, so here we would just say that the multivitamin population mean is going to be less than or equal to the control population mean. In other words, the multivitamin's not doing what it's supposed to be doing. So what we're going to do is we're going to assume that this is true, and then collect a sample, plot it on this distribution where this null hypothesis is true, and then see how likely it is. So here's our sampling distribution of means, and when we're dealing with the sampling distribution, a z-score refers to standard error. So when I showed you that formula for the z-score last time, it was based on dividing the mean minus the mean of means over the standard deviation divided by the square root of n, and that standard deviation divided by the square root of n thing is the standard error of the mean. I have it here. So we need a standard error A. I decided to be a little cocky, I guess, when I was writing these slides, and I have no idea why. But this is the standard error of the mean formula, and all that it is what's in the denominator for calculating the z-score. The standard error of the mean is taking the standard deviation that's given to us and dividing it by the square root of the sample size that's given to us. And you might be asking yourself, where did you get 15 and where did you get 25? If we go back to this example prompt, it says that the IQ scores are normally distributed, generally speaking, with a mean of 100 and a standard deviation of 15. So the 15 is our standard deviation for the population, and 25 is the sample size that we take. So to calculate the standard error of the mean, I decided to use friendly numbers this time. It won't always be that way. But the standard error of the mean, which is indicated here as sigma sub m, is equal to the standard deviation divided by the square root of the sample size. If we simplify that, that should be 15 over 5. And if we simplify that further, that standard error of the mean is 3. And when we go back to our distribution, here, fortunately PowerPoint let me do that. Each z-score is a standard error, and it's not a standard deviation, again. So when we're plotting this, the z-scores now correspond with each increment of 3 units of standard error. So we said that 100 is where the center of it is, and if we go up 1 standard error or 3, we go to 103 at the first indicator here. The second one, it's 106. The third one, it's 109. And then I guess it would be 112, and I'm off the screen now, just like this mean that we've observed of 114 is way off the screen. And remember, this is a distribution of sample means, but it's also a probability distribution. And the higher the peak at any particular point, the more likely that that particular observation should be. So if we're wrong, if the multivitamin doesn't do anything, we should expect something here. This is the most likely outcome to happen. We should just observe whatever the IQ score is on average. If we're right, and the multivitamin is doing something to IQ scores, we should observe something that's further and further away. And you can see that the mean that we observed is way in the tail, and we can calculate the probability that's associated essentially with that. But it seems like it's very unlikely, which is good for us, because then that says something about the probability of the observation and about whether or not we're correct, essentially. Step 3, we have to find the critical z-score. A critical value is essentially what value do I have to be more extreme than in order to say that I found support for my hypothesis. The critical z-score for alpha equals 0.05 is the same thing every time. What we're trying to do here is, here's our sampling distribution. We're trying to find where the 5% of this tail end of the distribution is here. So this is at z equals plus 2, 2%, and at plus 1, it's 16%, so it's somewhere in between these two things. But what we want to do is we want to know where is the critical region, as it's called, or where is the area that my score needs to fall into in order for me to say it's less than 5% likely that we would have gotten that observation. Stated differently, we need the 95th percentile, right? Because the 95th percentile tells us the bottom 95% and the top 5%, and we want the top 5% in this case. So we need our friend the z-table. Dearest z-table, please help my class solve the practice problem I created. Where is the critical value for alpha equals 0.05? Also, how are the kids? Love, Dr. M. I often write letters to tables. This is another thing that I probably should conceal from the other clinically oriented psychologists in the department, but it's a fun practice, so I continue to do it. Here's my letter to the z-table. Here's the z-table that we've seen in the past. And I've gone ahead and found the 95th percentile here. What we want to do, and I'll move the circle for a second just to illustrate where that came from, is we want to find where in the table is 95%. and we have to then figure out where the z value is for that. And the closest thing to 95% in this table turns out to be 1.65. You'll notice, and there was a question on the test about this to find the 95th percentile and asking you what x value corresponds to that, and to do that you had to find the z-score that corresponds to that. And to find that, what you have to do is you have to well, you looked in the table, and then some of you asked me, well, do I use 0.9505 or 0.9495? Both of them are the same distance from 95%. And I said, well, you can use either one. And some of you did, and that was fine for that example. Now I'm telling you, you have to use 1.65. And why? Why can't we use 1.64? Think about that for a second. Pause it if you have to, and then I'll answer this question. The reason that we have to use 1.65 is because if we beat 1.65, then we can be confident that we also beat 1.64. So going back to this distribution, if 1.65 and 1.64 are right next to each other on this z distribution, 1.65 is more extreme. And in order to reject the null hypothesis, we need something that's farther away from the mean. If we can be farther away than 1.65 here, then we know we're farther away from 1.64. If we're only farther away from 1.64, we don't know if we're really at the 95th percentile, because we could be at the 94.95 percentile, and therefore we're not at the 95th percentile. So you always use the larger value in cases to make it harder for yourself to reject the null hypothesis, to be more convinced that you actually did reject the null hypothesis. And if that point's unclear in class on Thursday, we can talk about that. So here's our sampling distributions of means for this example. I'm plotting the critical z-value here at 1.65, and everything above this here is the rejection region. If our observation falls within this region, or above this score, or is more extreme than this score, then we reject the null hypothesis. Unfortunately, we have a z-score here, and we have a sample mean of 114, which is not a z-score. And at this point, we are comparing apples to oranges if we compare a z-score to an x value. So what we need to do is we need to find out what the z-score is for our sample mean of 114. And I kindly worked out the math here already. So the z-score formula is you take the mean that you have for your sample, you subtract the population mean, this mu, and you divide it by your standard error of the mean, which we calculated earlier, which was 3. So when I rewrite this formula, our sample mean is 114, our population mean is 100, and then our standard error is 3. This simplifies to z equals 14 over 3, or 4.67. So I'm going to go back to this distribution. When we plot this point on the distribution, I have it pointing off screen because it's way out there somewhere, 4.67. Our observation is 4.67 standard errors above the mean. We could find the exact probability of that observation if we wanted to, but for our case, for rejecting the null hypothesis, all that we need to know is it less than 5% likely that it happened? And because it's out here, it is less than 5%. This area above this blue line, this critical z-score, is 5%. And our observed z-score, corresponding with our sample mean, is within that 5%, that tail end. So we would say that's very unlikely to happen if we're looking at this distribution where we assume that the null hypothesis is true. If we assume whatever's typical about IQ scores, that's a very unlikely z-score to happen. So we would want to reject the null hypothesis because it seems like something's going on here. So now we have to make a decision. We have two that we can make. We either reject the null hypothesis, z observed is further from the mean than z critical, or we fail to reject the null hypothesis. So in this case, that's what happened. The z observed score was further from the mean, so we'd reject the null hypothesis. A note about this, I'm going to be very picky about the language that you use. You will reject the null hypothesis or fail to reject the null hypothesis, and those are the only two series of words that you will use. Don't ever say accept the null hypothesis. Don't ever say accept the research hypothesis. Never say the null is false or the research hypothesis is true. We are not, in science and in statistics in particular, we're not dealing with absolutes. So we're not dealing with a situation where we say, I've absolutely proved that this multivitamin is effective. What about the fact that we selected a sample of Muhlenberg students? Maybe Muhlenberg students are just smarter than the population on average, and that's why we found what we found. And that pokes a hole in our logic. It's not the multivitamin if that's the case. It's the sample that we used. So because we're dealing with probability, we talk about rejecting or failing to reject the null hypothesis with the understanding that we're going with what probability tells us is the most likely thing to be true, or the most likely thing to have happened, or the most likely to, with our research and null hypothesis, be the case. And the last thing we do is we have to state our conclusion. Breaking this, so I'm going to read this to you and then I'll break it down. It says, a one-sample z-test was conducted to determine if the multivitamin increased IQ scores. So the first thing we're doing here is we're identifying the test that we used. This is a one-sample z-test. It's the first of many types of tests we're going to be talking about in this class, and it's the easiest one to do. It's the most basic one. It's the kind of test that you do when you assume and know what your population mean and standard deviation are. And so IQ scores are a good example of this because we have many, many, many IQ scores, so many so that we know what the population mean and standard deviations are. A lot of times we don't know what those things are, and we wouldn't use a one-sample z-test in that case. Results of the test were significant, z equals 4.67, p less than 0.05, leading us to reject the null hypothesis. So here I said results of the test were significant, so the test is what we're describing as significant, rather the results of the test are what we're describing as significant. We report in italics the z-score. Italicized z equals 4.67, italicized p is less than 0.05. We don't know right now what the exact probability is. We could find it if we wanted to, and then we could report that if we wanted to. Also note that to be consistent with APA style, you need to report things to the second decimal place, which is why I've been asking you to do that all along. APA style is the American Psychological Association's way of writing papers, so this is consistent with APA style. Our sample of 25 college students had significantly higher IQ scores from the population mean. So we're basically restating what our original hypothesis was, but now it's not a hypothesis anymore, it's something that we found. And we're not saying that the multivitamin absolutely will work on everyone and increase their IQ. We're simply saying that in our sample, our mean was higher, so much so that it was significantly higher. So we justify why we reject the null hypothesis here. And that's really all that we can say right now. This might leave you wanting more information. And on Thursday, we're going to talk about some nuances of this, how we can get more information. For instance, what we don't know is how much, in this results anyway, what we don't know is how much should we expect IQ scores to increase if you start taking this multivitamin. We have no idea. We know what our sample mean is relative to the population mean. We don't know if the sample mean is what the population of people who take the multivitamin looks like. It's only 25 people, so there might be some error there. But we can maybe try to use some statistics to come up with an answer to that question. There's also some other issues that we'll talk about, some nuances associated with hypothesis testing, but this is just a very basic introduction to hypothesis testing. I'm going to go ahead and post the slides onto Canvas for you. And this brings us to whether or not we're going to have a pop quiz. I'm sure some of you were under the impression that well, if it's online, there's no way he can flip a coin. It turns out that I can, because there's this handy website that just says justflipacoin.com, I believe, and if you click on it, it'll rotate the coin. Right now it says heads. I'm going to flip this coin twice, once for the morning class and once for the afternoon class, like I normally would, and that will determine whether or not you have a pop quiz. I'll post the quiz on Canvas and give you a generous amount of time to complete it. It'll probably have about 5 questions. I haven't written it yet, but it'll be about last class's content. So here we go. For the morning class, I'm going to click this. If it's heads, you guys have the quiz. If it's tails, you don't. Okay, so morning class, you guys have a quiz. So I'm going to post the quiz for you guys on Canvas. Afternoon class, you do not have a quiz. That's just the way the coin flip works. This is a fair coin. It's based, although it's a digital coin. But I'll post the questions for the quiz on the afternoon classes section. It won't count for anything, but you'll be able to take it and check your answers to see if you're kind of getting the content. Morning class, it'll count for you guys, and I'll give you guys until Thursday to complete it. So that's it for today. If you have questions, please contact me. Don't hesitate to contact me through email or other means. I'm happy to answer your questions for you. And I will see you guys on Thursday.